This is Cycle 1, Lesson 1 of the Grade 11 University math course called Functions, and we're going to review some properties of quadratics quickly here. Graph of a quadratic relation is called a parabola. Parabola, there we go. It's the vertex of a parabola. That's the point with the greatest y-coordinate if the parabola opens down. So if it opens down, right, like this, then the highest point is the vertex. If it opens upward, like this, then it's the lowest point that's going to be the vertex. When a parabola models a real situation, the vertex is called an optimal value. And it's a maximum when the parabola opens down, and a minimum when the parabola opens up, for the reasons we just talked about. The direction of opening can be found from the sign of the second differences. So if we're looking at a table of values and we calculate the second differences, then if it's a positive bunch of second differences, then the direction of opening will be up, and if it's a negative set of second differences, it'll open down. A parabola is symmetrical with respect to a vertical line through its vertex called the axis of symmetry. The axis of symmetry is the perpendicular bisector of any 2 points on the parabola that have the same y value. If the parabola crosses the x-axis, the x-coordinates of these points are called the zeros or the x-intercepts. And the vertex is always directly above or below the midpoint of the segment joining the zeros. So let's just think back to what we know about a parabola. This is our most basic parabola, y equals x squared. Think about making a table of values just so we can think about what some points would be on our most basic parabola here, x, y. Let's just pick some x coordinates around the origin. So if I square negative 2 times negative 2 is positive 4. Negative 1 times negative 1 is positive 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So what we get if we plot these points is negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. It makes this U shape. And I could carry on. I could do negative 3 squared would give me positive 9, just as positive 3 squared would. So when I connect these dots together, I get a nice smooth curve, at least as smooth as you can draw it, and I have limited artistic ability. And that's the shape, right? That's the parent function. This is y equals x squared. And by parent function, we mean the most basic parabola out there. Any other parabola, any other quadratic is going to be this with some other numbers added on. How can we tell if a relation's quadratic? Well, we can look at the table of values for starters. First differences, this table is supposed to be set up like this. So in other words, if I take 2 and, well, actually, let's put it this way. If I'm at 3 on the y-axis and I go to 2, I'm going down by 1, right? So going down by 1 would be negative 1. And if I'm at 2 and I go go up again to 3, I'm going up by 1 now. And then if I go from 3 to 6, I'm going up by 3. And so hopefully you see the pattern there. From 6 to 11, I'm going to be going up by 5. And I don't have to write the plus signs if I'm doing positive numbers. It's assumed to be positive. But anyway, there's my first differences. For my second differences, if I do the same idea where I'm just subtracting one from another. So if I let's put it this way. It's easier to think about it this way. If I'm at negative 1 and I go to positive 1, I'm going up the number line by 2 units, aren't I? And then if I go from positive 1 to positive 3, I'm going up by 2 units again. So 3 to 5 is up by 2, 5 to 7 is up by 2, and so there's my second differences. So I'm taking the differences of the differences. Let's do our scatter plot. So if I was to graph all these ordered pairs, like 0, 3, for example, well, there's that point there. And then if I were to graph 1, 2, then I'd have my next point. And so you should be pretty familiar with graphing ordered pairs by now. I have the point 2, 3, and 3, 6, and 4, 11, which is off my graph, but I'm going to pretend I can see where it is. It's up there. And 5, 18, well, that's going to be even higher. I mean, I'm just guessing, but it's going to be up here somewhere, isn't it? Is it appropriate to include a line of best fit? Well, a line of best fit would be something like this. Line means a straight line. I think we can do better than a straight line. I would say, no, this data isn't linear. In other words, it doesn't really form a straight line. It's nonlinear. So it forms a curve. So again, it would make more sense to draw a parabola for this data. Probably. I mean, assuming it's quadratic. The first difference is no consistency or no pattern. But for the second differences, they are all equal. So they're all constant is the word that we often use. When data is nonlinear, we use a curve of best fit instead of a line of best fit. When the first differences are constant, the graph is linear. So the rate of change is also going to be constant. When the second differences are constant, the graph is quadratic. The degree of the polynomial is the highest exponent that appears in any term of the expanded form of the polynomial. So quadratic is degree 2 because the highest exponent is a 2. A polynomial of degree 2 is quadratic relation, as I just pointed out. The equation. A quadratic can appear in the following forms. It can look like this, which is standard form. So for example, y equals, let's just make one up. Let's see, how about x squared plus 6x plus 9? That would be standard form. Or we could see it in factored form, like this, in which case it would be something like y equals x plus 3 times x plus 3. That would be factored form. Or we could see it in vertex form. And vertex form looks something like this. I won't try to make them all match, but it might be something in the form y equals, let's say, x minus 2 squared plus 3. That would be an example of vertex form. These aren't all equal to each other, but they're just 3 different forms. If the exponent is 2, if the exponent is 2, we know it's a parabola or it's a quadratic. If a value is greater than 0, the parabola opens up and has a minimum. What do I mean by that? Well, the a value, remember, is the number in front of, at the very beginning, right after the equal sign in front of the x, whether it's whatever form it's in. So this is assumed to be a 1 here, assumed to be a 1 here, assumed to be a 1 here. Those are all positive ones. In every one of those cases, a is a positive number. And if it's a positive number, the parabola opens upward. And if parabola opens upward, as we've already seen, it's going to look something like this, which means that the vertex is going to be a minimum, as we can see here. If A is negative, less than 0, that means the parabola is going to open down, and it's going to have a maximum. Again, I've drawn this before, higher up, but there's a parabola opening down, and there's it having a maximum value. The value of x that makes a times x minus s times x minus t equals 0, or the values, are called the zeros, as I pointed out above, and these are the x-intercepts of the graph. The zeros are therefore blank and blank in this example, and the x-coordinate of the vertex is found using, well, in this example, I guess what we're referring to by this example, we mean in the general form, they're going to be s and t, whatever numbers are in the place of s and t in the formula, or when we see an actual equation. And the x-coordinate of the vertex is found using it's going to be s plus t divided by 2. So it's going to be halfway between the s and t, halfway between the two zeros. As we know, the vertex is on the axis of symmetry, as we can see in this sketch here. And if this is 1, 0 here at s, and this is another 0 here at t, then if I take the average of them, s plus t, divide that by 2, that's the average, that'll give me this point right here, which is going to be the x-coordinate of the vertex. When s and t are known, a can be found by substituting in a point, an xy, an ordered pair point, to be known on the parabola. Then we can calculate what a is. So let's see if we can sort of run through an example here. Consider the relation to the right, state the zeros. Well, the zeros are at 6 and 8. State the direction of opening, down. State the equation of the axis of symmetry. Well, the axis of symmetry is this vertical line here, which is halfway between those two zeros. So again, it's the average of the zeros. So it's going to be axis of symmetry is 6 plus 8 divided by 2, which is 14 divided by 2, or x equals 7. State the vertex. That's going to be, I'll do this one in red. That's this point here, which is 7, 1. It's an ordered pair. State the max or min value. That's just the y-coordinate of the vertex. So the max or min value is just this 1 from the vertex. State the domain and range. Domain is what x values are possible. So if we look at this parabola, we can assume there's arrows on the bottom, so it's going on forever. And it's going to go out to the left forever, it's going to go out to the right forever, so the domain is all real numbers. The range is going to be what y values are possible. Well, it's got a maximum value at a y value of 1. It can't go above 1. So that means that's a limit there. But it can go down forever. So the range is all real numbers as long as it's less than or equal to 1. So that's my range. Consider this example. State the zeros. Okay, let's do it again. -3 and 2. Notice how I'm not writing them like an ordered pair. Sometimes people will write it like this. That's not right. If you think about it, that point is actually, that would be a point up here. That's the point -3, 2. We don't want that. So I'm writing -3 and 2. There's a difference. Direction of opening is up. The equation of the axis of symmetry, well, if I do -3 plus 2 divided by 2, then that's -1 divided by 2, or -0.5. So the axis of symmetry is going to run right down between -1 and 0. The vertex appears to be, and in this case I'm just estimating, but it appears to be at -0.5 and negative 6.25. I'm going to go with 6 1/4. State the max value. Again, well, in this case, the min value, but it's just the y value of the vertex, so negative 6.25. State the domain and range. Again, this parabola goes on forever, and the x values, the domain, are all real numbers. In other words, there's no limit to how far to the left or right it'll go. The range is all real numbers, but again, there is a restriction. It can't go below this vertex, can it? And if the lowest point is negative 6.25, then y has to be greater than or equal to negative 6.25. That's it for this lesson. Give the practice questions a try now.